And now recording. All right, so I'm going to do a few more problems on L'Hopital's rule and then start 4.5, which is really just more curve sketching. And so schedule-wise, we're sort of where we belong. Remember, we're not scheduled to do any of 4.6, so I made a mistake here. So we're actually semi ahead, perhaps. Okay, so 4.4 was L'Hopital's rule. 4.5 is more curve sketching, including the calculus and the pre-calculus. Now, some of the things that you did in pre-calc, that comes back in 4.5, and in addition to the calculus stuff. Okay, and again, admittedly, a lot of these problems tend to get really long. I intentionally handpicked these problems because they're good problems, but some of them can get really long. So again, I keep that in mind on a test. I mean, on a test, you only get an hour, and I realize a really good problem can already take a long time. So I'll have to keep that in mind when I give you the next test in terms of, okay, if you do a full-fledged problem from beginning to end, it either has to be done fairly quickly, or I'll just have you do a portion of it. Okay. All right, so let's get back to some more L'Hopital's rule, some interesting things. So problem 53 in 4.4, which looks like this: temporarily ignore the red. Limit x approaches 0 from the right of 1 over x minus 1 over e to the x minus 1. Okay, and I can't do anything with this until I combine the two fractions, right? So the original had 1 over x minus 1 over e to the x minus 1. So I get a common denominator, which basically means the right side needs the left and the left side needs the right. So this side multiplied by e to the x minus 1 over e to the x minus 1. And this side I need x over x, right? So that way my common denominator is x e to the x minus 1. Okay, then I work out the top. It's nice multiplying by 1, right? When you multiply by 1, you're not doing anything. So it's e to the x minus 1 minus x. Okay, so the new expression is this. And I notice I do get 0 over 0. Okay, so if I plug in 0, e to the 0 is 1. 1 minus 1 is 0, minus 0 is 0, so the top is 0. Put a 0 there, that's 0, so you definitely have 0 over 0. So I can do L'Hopital's rule. Okay, so L'Hopital's rule says if you have 0 over 0 or infinity over infinity in a limit, take the derivative of the top, take the derivative of the bottom. Don't do the quotient rule. Okay, it's easier than the quotient rule. Just differentiate the top and the bottom. So the derivative of the top is e to the x, that's nothing, minus 1. The derivative of the bottom, unfortunately, you need to do a quotient rule. First function, second function. So first x times the derivative of the second. Derivative of e to the x minus 1 is e to the x, plus the second, e to the x minus 1, times the derivative of the first, but the derivative of x is just 1, so I don't have to write anything after that. All right, and it looks like we again get 0 over 0. If I plug in 0 to the top, I have 1 minus 1. Put a 0 here, that's nothing. And well, that's going to be the same thing, 1 minus 1, which is 0. So I can do L'Hopital's rule again. Okay. And what is LHR? It's L'Hopital's rule. It's my abbreviation for I'm doing L'Hopital's rule. By the way, if you don't put LHR on a quiz or test or homework, I'm not going to take off points. I didn't do it all the time either. That problem where we had to do it 4 times yesterday, I didn't write it because after a while, I didn't feel like it. Okay. But if you want to write it, that's fine. And let's just say if you write LHR and you happen to get the problem wrong, I might be more willing to give you partial credit. So at least I know what you were doing. So, oh yeah, you were thinking about L'Hopital's rule. You just messed up over here somewhere, so I can give you partial credit. Okay. So I differentiate again. So the derivative of the top is e to the x. And by the way, even at this stage, I know I don't have to do any more. So what do you mean you don't have to do any more? If I plug in 0, I get e to the 0, which is 1. So for sure, I'm not going to get 0 over 0 or infinity over infinity. So definitely, I don't have to do L'Hopital's rule anymore after this step. Now, the derivative of the bottom is going to be a little bit more work. So that looks like a product rule, right? So first, x times the derivative of the second, derivative of e to the x is itself, plus the second, e to the x, times the derivative of the first, which is 1, plus the derivative of e to the x is itself, and derivative of negative 1 is 0. Okay, so I have this. Now, when I plug in, I can determine it pretty easily. Okay, so put a 0, that's 1. 0 is 0, and that's 1 plus 1. So 1 over 1 plus 1, 1/2 is my final answer. Okay. So that was 53. And that's all on this piece of paper. I've already shown you this other thing here. So let me go back and give you the focus thing again if you want to look at the video later. Okay, and that's that. All right, then the last few problems on L'Hopital's rule that I was going to show you. Indeterminate powers. So if you look at 57 and on, 57, 59, 61, 63, 65, they've got some strange exponent thing there. Okay. We actually tackled this theme before. Okay. How do I get those exponents down? I take a natural log, right? So there has to be something involving natural log. So if you want to put this down in your notes, 57 through the rest, 65, there's some ln going on. There's no special name for it. Okay, but to get those exponents down, we take the natural log. And I'll show you how to do that for a couple of them now. All right, so 59. 59 here. Limit as x approaches 0 of 1 minus 2x raised to the 1 over x. Okay, you know you can't plug in directly, right? You got 1 over 0, which is infinity, so to speak. That's going to be 1. Okay, what you got to do is get that exponent down. So here's how you do it. First, call the original y. Y equals 1 minus 2x to the 1 over x. So ultimately, I'm trying to find the limit as x approaches 0 of y. Okay, it's important to have that because we're going to need that a little bit later. Okay, so I'm going to call that thing y instead of calling it the mess. I'm saying limit as x approaches 0 of y. All right, so y equals this. Take the natural log of both sides, that theme again. So ln y equals ln 1 minus 2x raised to the 1 over x. As soon as I do that, the 1 over x comes down in front. But if we're multiplying by 1 over x, you might as well just say divided by x. Is that right? So do you agree mathematically that's the same as that? Okay, so one more time, the 1 over x comes down. So it's 1 over x times blah, blah, blah. But if we multiply by 1 over x, it's the same as dividing by x. And now there's the quotient that I want. I got something divided by something. So now I take the limit as x approaches 0. The thing is, I'm not taking the limit as x approaches 0 of the original. Okay, I'm taking the limit as x approaches 0 of the natural log of y. So when I get my answer, blah, blah, blah on this side, I don't have the limit of the original. That's why I write down, I want the limit as x approaches 0 of y. I'm figuring out the limit as x approaches 0 of ln y. But you know what to do after that, right? How do you get rid of the ln? Exponentiate. So I'm going to exponentiate my result from over here. All right, so I got the quotient that I want, something divided by something. This is 0 over 0. Limit is x approaches 0. If I plug in 0, I have ln of 1, which is 0, and the bottom is 0. So I can do L'Hopital's rule. Derivative of the bottom is 1. That's easy. Derivative of the top is 1 over 1 minus 2x times negative 2. And then I just drop that 1 there because, you know, if you divide by 1, you just forget about it. So limit as x approaches 0 of negative 2 over 1 minus 2x. Okay, now you can just plug in 0, you get negative 2 over 1, which is negative 2, which is not my final answer. But remember, that's why I wrote this down. I now have limit as x approaches 0 of natural log of y is negative 2. But ultimately, I'm looking for the limit as x approaches 0 of y. I do have the limit as x approaches 0 of ln y. So how do I get rid of the ln y? Exponentiate. So put the e there. Okay, that way the e cancels out ln. So I have what I want. Limit as x approaches 0 of y. Ultimately, that's what I want. Find the limit as x approaches 0 of y, because I declared y to be this whole thing. Limit as x approaches 0 of 1 minus 2x to the 1 over x. I called that y. That's what I want. So here it is. Limit as x approaches 0 of y is e to the negative 2 power. Okay, so that's what I have. All right, I was going to show you one more of that type, 65, the last one, and then that's it. So there were, I think, 5 problems of that type. Yeah, 57, 59, 61, 63, and 65. Okay, so I'll show you 2 out of the 5. All right, limit as x approaches 0 from the right of 4x plus 1 raised to the cotangent of x. Okay, you know that's really messy, and I don't like that cotangent up there. So I got to get that cotangent down. So how do I get that cotangent down? Using an ln. Okay, so same protocol. Let y equal this expression, 4x plus 1 to the cotangent of x, which means ultimately I'm trying to find the limit as x approaches 0 from the right of y. All right, so now I'll take the natural log of both sides, ln here, ln y. ln here, once I put ln here, cotangent comes out in front, right? So ln y is cotangent natural log of 4x plus 1. Write cotangent as cosine over sine. So natural log of y equals cosine x ln 4x plus 1 over sine x. So there's the quotient that I want, right? In order to do L'Hopital's rule, it has to be a fraction, something divided by something. So you have to force it sometimes. All right, just like the previous problem, limit as x approaches 0 from the right of natural log of y. So when I do blah, 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 again, I'm not getting the answer to the problem. I'm getting the limit of ln y. Ultimately, I just want the limit of y. So how do you get rid of the ln? You have to exponentiate, put an e there. All right, I claim this is 0 over 0. Let's see why. If I plug in 0, let's see, ln of 1 is 0, so 0 times that is 0. And I know from trig, sine of 0 is 0, so it is 0 over 0. So L'Hopital's rule applies. Take the derivative of the top, derivative of the bottom. Let's get the bottom first, because that's the derivative of sine is cosine, right? This one's harder. That's a product rule, right? Cosine x, ln 4x plus 1. So let's use the product rule. First function, cosine x, times derivative of the second. So derivative of natural log of 4x plus 1 is 1 over 4x plus 1 times 4 by the chain rule, plus the second function, ln 4x plus 1, times the derivative of the first, derivative of cosine x, negative sine x. Now I'll plug in. Let's see, cosine of 0 is 1 on the bottom. If I put a 0 right here and here, sine of 0 is already 0. So this thing becomes 0. This thing is all wiped out. Okay. That whole thing is gone. Put a 0 there, cosine of 0 is 1, times 4 divided by 1, 4. So I have 4 plus 0 over 1, which is 4. Okay, so I have the limit as x approaches 0 from the right of natural log of y is 4. Okay, but that's not my final answer. I need the limit as x approaches 0 from the right of y. I have the limit of ln y. So once again, to get rid of that ln, put an e. So e here, e here, e and ln cancel out. So I have the limit as x approaches 0 from the right of y. And just to remind ourselves what I was really doing, what was y? Y was this original, the ultimate original question. So limit as x approaches 0 from the right of 4x plus 1 raised to the cotangent of x. Final answer is e to the 4th power. So there we go. All right, and that's as much of L'Hopital's rule as I wanted to show you. If I have time later today, I was going to give you an in-class assignment involving L'Hopital's rule. Okay, it won't be a very complicated one. Hopefully it's easy enough that you can get. Okay, and I think I'm done with that section. So I'm done with the paper. Let me go back and do my focusing thing again. So 59, raising up the paper again, in case what I showed you was too blurry. Okay, and then 65. And that's that. Okay, so that's as much of L'Hopital's rule I was going to go over. So I'm done for now for 4.4, and I'm ready to start 4.5, the next section, which is actually not really a new section. It's more curve sketching. Let me just go ahead and show you problems that we had from it. Let's take a quick look at this again. So I'm pretty much right on par right now, starting 4.5. There's a lot of good problems here. We just don't have time to do them all. So it looks like just about every other odd until 41 and 45. So 45 was the highest problem. So it's more curve sketching. So page 321. Okay, so for those of you who don't have the book and aren't getting it, 5, 7, 1 through 9, 11 through 17. And on 322. Many more. And I think 45 was the last one, I believe. So I forgot, but I think that, yeah, that pretty much should do it. By the way, why are we skipping 4.6? Graphing with calculators and calculators, right? So that's if you were to use a calculator or a computer. I'm not forcing you to have a graphing calculator or to use a computer for graphing. So that's the reason why I'm deciding to skip that section. Okay. All right, so what are we covering in this section that we didn't before? Okay, so guidelines for sketching a curve. So I'm on page 315. We have domain to consider, intercepts, figure out what happens when x is 0, y is 0, symmetry. Okay, remember even and odd functions, you had that in pre-calc, hopefully. Asymptotes, page 316. Asymptotes, horizontal and vertical asymptotes. All right, that was all pre-calculus stuff. Okay, so again, starting on 315, domain, intercepts, symmetry, and asymptotes. You say, how come you didn't consider them before? You actually should consider them all the time. Okay, we kind of referred to them a little bit before, but we're emphasizing a little bit more now. So back on 316, asymptotes, and then the calculus stuff. E, F, G, and H, intervals of increase and decrease, local max and min, concavity, points of inflection, sketch the curve. Okay. All right, so that's what's happening. There was a question in the chat about how do you know to turn back to Y? The last two problems that we did for L'Hopital's roof, in particular, I think this is answering a question for 59. When you're trying to do a limit, with, especially with L'Hopital's roof, this doesn't look like a fraction, right? But you see that weird exponent for 59 and also 65. So that's when you know there's going to be an ln thing going on. So that Y be that. It's only going to look nicer when you do the natural log of both sides. Okay, so that was for 65 and also for 59, right? Take the ln of both sides. Then you say, okay, I get something nice, but I only got it nice when I did the ln of Y. Okay, but the original problem wasn't with the ln Y, it was with the Y, with Y. So that's why in problem 59 and also 65, you have to switch back. I think that's answering your question. If not, ask again or send me an email or come see me during office hours. But yeah, specific for those last 5 problems that I mentioned, what was it, 57 to 65, I think it was. But those problems that are like that, involving L'Hopital's roof, where you had to get that exponent down, then you say, okay, I need to do ln of Y. But you don't want ultimately ln Y, you just want Y. So at the last step, you have to exponentiate. Okay, so that's my guess of what you're asking. Okay, so now for full-fledged curve sketches, we're going to try to analyze all this stuff. Okay, so 4.521. Y equals x minus 3 times radical x. What does the graph look like? And by the way, don't memorize, that list. If you need it, I'll give it to you. Or of course, you can put it on your cheat sheet. Okay, what's a domain? Well, I see a square root. That automatically tells me something. Once there's a square root, and again, we're only doing real math, no imaginary stuff, no complex numbers. I'm not allowed to put in what kind of a number? Negative. So domain is 0 to infinity. Okay, so whatever the graph looks like, I can't have anything in quadrants 2 and 3. Okay, I'll just show you quickly for the graph. There's nothing over here. Can't, because you're not allowed to plug in any negatives. Okay, intercepts. Okay, when I plug in 0, I get 0. How about y equals 0? How do you make all of this 0? Well, that would be 0 and also 3. So my intercepts are 0, 0, and 3, 0. Symmetry is automatically none. You might recall from symmetry, you replace x with negative x, but that's not possible, right? If you plug in a positive number, you can't plug in a negative number. So it's automatically no symmetry. Asymptotes, there are none. There's no trig function to worry about. There's no denominator to worry about. Okay. You can talk about end behavior. What happens when x goes to infinity? When x gets big, that gets big, that gets big. Big times big is big. So it shoots to infinity. So when x gets big, y gets big. When x goes way out here, y goes way out here. Okay. I'm not allowed to go toward negative infinity, and the graph stops going to the left at the origin. Right? You can't go past the origin. So there's no asymptotes. All right, so now I'm ready for my calculus part. So do my first and second derivative test. All right, so to differentiate this, I can avoid the product rule if I distribute. This is x to the 1 times x to the half, right? It gives me 1.5 or 3 halves minus 3x to the 1/2. Okay. All right, so the first derivative would be 3 halves x to the 1/2 minus 3 halves x to the negative 1/2. Then do the double prime. Second derivative is 3/4 x to the negative 1/2. And let's see, negative times a negative is positive 3/4 x to the negative 3/2. And then I just decided to clean that up a little bit. Okay, this is 3/4 x to the 1/2. This is 3/4 x to the 3/2. And I noticed this is always greater than 0 for all x greater than 0. Okay, my domain is only from 0 to infinity. I'm not allowed to plug in 0, but if I plug in any positive, this whole thing is positive for sure, right? So I can do a second derivative analysis very easily. The function is concave up from 0 to infinity, and it's concave down nowhere. So automatically there's no inflection point. So whatever this graph looks like, it's got to be concave up all the time, as you can see here. All right, so I'm going to set y prime equal to 0. So y prime way back here was this. I'm going to rewrite this as 3/2 radical x minus 3/2 radical x, like that. Okay, that one was x to the 1/2. This is x to the 1/2 with square root of x on the bottom. Okay, set it equal to 0. That's a minus there. Move that over. You can cross off the 3/2, right? Or just say multiply both sides by 2/3. Gone, gone. Cross multiply. Get radical x equals 1 over radical x. X equals 1. Radical x times radical x is 1, right? Okay, plug in 1. 1 minus 3 is -2. Square root of 1 is 1. I have 1 comma negative 2. Now, I could make a sign chart, but I don't have to. I already know the graph is always concave up. So if I have concave up, the second derivative test tells me when I have a derivative of 0, it's automatically going to be a minimum. Okay, so I have a minimum point right here. So there we go, I got it. So f is decreasing from 0 to 1 and increasing from 1 to infinity, which means 1 comma negative 2 is a relative minimum. Again, relative or local, same thing. And in this particular case, it's also an absolute minimum because all the graph does is it goes down and it goes back up. Okay, so here we go. Here's the whole graph. Origin goes down to 1, negative 2, relative min and absolute min, comes back up, touches 3, 0, goes up forever, always concave up, never concave down, no inflection points. Okay. All right, so that's the way that one goes. Okay, next one I wanted to show you was 41, way over to 41. I have other problems to show you too, but I want to give you at least these for now. Let me double check myself here. Okay, 41 says y equals arctangent of e to the x. 41. And arctan is the same thing as inverse tan. So if they write it as tan to the -1, that looks like it's the same thing. So arctan e to the x, the same as inverse tangent e to the x, problem 41 there. Okay. Okay, the domain is all real numbers. You're allowed to take arctangent of anything, and you can take e to anything. So e to anything comes out to be a real number. And you can take its arctangent. So the domain is all real numbers. Intercepts. Well, plug in 0. E to the 0 is 1. Arctangent of 1 is pi over 4. Okay, because the tangent of pi over 4, 45 degrees, is 1. So the only intercept is 0 comma pi over 4. Okay. Now I would say, what about y equals 0? That actually can't happen because you know e to the x is always positive. Okay, so how do I get 0 here? I know arctangent of 0 is 0, right? Arctangent of 0 is 0. So I ask myself, what number makes this 0? Well, it can't. E to the x is always positive. Okay, so this graph never touches the x-axis. All right, is there any symmetry? F of negative x, if I put negative x after arctangent of e to the negative x, that's not the same as the original. That's not the opposite of the original. So there's no symmetry. At least I should say no symmetry with respect to the x or y axes. Asymptotes there are. When x approaches infinity, you know this gets big. Okay, we saw this before, but arctangent of a really, really big number is close to pi over 2. So when x approaches infinity, y approaches pi over 2. How about x approaches negative infinity? E to a negative big number is almost 0. And we know arctangent of 0 is 0. Okay? So my asymptotes are 2. I have horizontal asymptotes, HA horizontal asymptotes, y equals 0 and y equals pi over 2. Y equals pi over 2 and y equals 0. So when I go way out that way, I approach pi over 2. When I go way out that way, I approach 0. Okay. So remember, arctangent of a super big number is close to pi over 2. I think I showed this to you before, but I'll demonstrate to you on my calculator. So first make sure that I'm in radian mode. Okay, so radian mode. Okay, so inverse tangent, same as arctangent. I'll just type in a super big number. I'm just typing 1.57, and then let me hit pi over 2, pi divided by 2. The last digit was off. 1.57079632678 for inverse tangent of that super big number. Pi over 2 has a 9, but I bet if I put some more zeros, it would get even closer and closer and closer. Okay, so yes, inverse tangent of a super big number is very close to pi over 2. Okay, so those are my asymptotes. All right, so now I'm ready for my calculus part. So find y prime. How do you differentiate arctangent? Goes 1 over 1 plus this thing squared, right? Derivative of arctangent, you might recall. So 1 over 1 plus e to the x squared. Then by the chain rule times derivative of e to the x, which is e to the x. Okay. So e to the x over 1 plus e to the 2x. Okay. So reminder on the derivative of the arctangent function. Let's see. I'm going to spend time to go back for that. So arctangent function. That was what section? 3.5, page 214. 3.5. Sure, I can get the book there. There's inverse tangent. 1 over 1 plus x squared. So we have a function, it's 1 over 1 plus the function squared. So 1 over 1 plus e to the x squared. And then times the derivative of e to the x, which is itself. So there's my y prime. Y double prime, unfortunately, is not very nice. Okay, well, the bottom is 1 plus e to the 2x squared. That's easy. Okay, the numerator, bottom times derivative of the top, derivative of e to the x is itself, minus the top, e to the x, times the derivative of the bottom. So what's the derivative of the bottom? Derivative of 1 is 0, derivative of e to the 2x is itself times 2. Okay, I'm cleaning this up. Distribute e to the x times 1. E to the x times e to the 2x is e to the 3x. Minus 2 e to the 3x. Which gives me e to the x minus e to the 3x over 1 plus e to the 2x squared. All right, set y prime equal to 0. Where was my y prime? It's over here. Can't. This thing's always positive for all x. Okay, remember, e to the x is always positive. E to the 2x is positive. Add 1, it's positive. Positive divided by positive, positive. So this graph is always increasing. It's always going to go up. So f is increasing from negative infinity to infinity. F is decreasing nowhere. Again, my abbreviation for increasing is arrow up and to the right. That saves me and you from writing I-N-C-R-E-A-S-I-N-G. And decreasing is an arrow down, so you don't have to write D-E-C-R-E-A-S-I-N-G. If there's no, if the graph is always going up, it's never going down, that means automatically there's no maximum. How about y double prime equal to 0? So here was my double prime. Set that equal to 0. It's not as hard as you might think. Okay. When is a fraction equal to 0? Top is 0. So e to the x minus e to the 3x equals 0. Move over the e to the 3x. E to the x equals e to the 3x. Divide both sides by e to the x. This gives you 1, right? That divided by that is e to the 2x. So temporarily ignore the ln. 1 equals e to the 2x. 1 equals e to the 2x. Take the natural log of both sides. ln of 1 is 0. ln e cancels out. 2x equals 0. X is 0. So if 0 comma pi over 4, which was the intercept, is a critical point for the second derivative. Okay, then I picked a number on this side, like -1 and 1. Now, the bottom is always positive, right? No matter what. There's a square there. Okay, if I plug in -1, this may not be that obvious. If I plug in -1, I have e to the -1 minus e to the -3rd. That's actually positive. This is bigger than this. This is like 1 over e, right? 1 over 2.7. This is 1 over 2.7 cubed. So this one's going to be bigger. So if I subtract, it's positive. Okay, then if I plug in 1, again, the denominator is already positive. I have e to the 1 minus e cubed. Okay, 2.7 minus 2.7 cubed. 2.7 times 2.7 times 2.7, that's like 20 something. So this is bigger. So if I subtract, it's going to be negative. So here we go. F is concave up from -infinity to 0. Concave down from 0 to infinity. And 0, pi over 4 is indeed an inflection point. And I'm ready for the entire graph. So here we go. Okay. Define for all real numbers. No symmetry. Only intercept is 0, pi over 4, which happens to be an inflection point. Asymptote, y equals pi over 2, horizontal asymptote. Another horizontal asymptote is the x-axis, y equals 0. Always increasing, concave up, concave down. And there we go. Okay, so let me go back and show you for focusing purposes. Otherwise, that's all I was going to do for today, and I was going to give you something to do in class. Not a curve sketch, that takes too long, but just a L'Hopital's problem. Okay, so that's what we're up against for section 4.5. And there's 41. I'll show you more tomorrow, of course. And some of you joined late. So remember, anytime you join late, go ahead and put your name in the chat so I can get you for attendance, because usually once I finish second row at 9:10 or 9:11 or something like that, then I put it away. I don't want to take it back out until after I'm finished. Okay, so that's that. All right, I think that's it. Anybody have a quick question about anything? If you ask me or you put something in the chat, I think I got it. Okay, any quick questions? Otherwise, I'll give you something to do in class. And that's it for today. Okay, so here we go. It's a L'Hopital's root problem. Hopefully it's not too bad. I'll hold this up for maybe 15, 30 seconds. Find limit as x approaches 0 of 1 minus cosine x over x. When you're done, put your answer in the chat and you may leave. It is a L'Hopital's root problem. Okay, if you have absolutely no idea what to do, check to see if it's 0 over 0. It is. Otherwise, it wouldn't give it to you, which means take the derivative of the top, take the derivative of the bottom, and then you can plug in. So hopefully it's not too bad. Okay, so again, it's limit x approaches 0 of 1 minus cosine x over x. Okay, so either do a screenshot or take a picture on your cell phone. I'll give you maybe just 10 more seconds and I'll make it disappear. But if it helps you, I'll also put it in the chat. I don't know why it keeps blinking back and forth between yellow and white there. Okay, so limit x approaches 0 of 1 minus cosine x over x. Okay, so what's the limit using L'Hopital's rule? You can just type the answer. Now, if I give you a quiz or test, I want to see your work. I want to see what the derivatives are of the top and bottom, but ultimately just, type it for in-class assignments, and that's about it. Okay, I think everybody should have it now. All right, so I'll make this disappear. Yeah, show that L'Hopital's rule works, plug in. You should get 0 over 0, and then take the derivative of the top and the derivative of the bottom, look for the same limit, and then go from there. Okay, I will assume that you all have it, so I'll stop the share, but I'll also type it in the chat, and then you can go. I'm going to stop recording also.